First place we'll start is oxidation states. So after talking with 151 instructors and then reviewing course competencies and all that fun stuff, you never learned it. So oxidation numbers and oxidation states is something that I guess they've decided has to appear only in 152 and not anywhere else. So that would be why no one heard about it, which I find shocking because I taught it in 130. And still teach it in 130. And I have since gone back and looked at the competencies for Chem 130. It's also not in Chem 130. So I have to change all sorts of things about my teaching. Number one, we got to make sure you guys are good with oxidation states. You guys think you got it sort of figured out at this point? A little bit shaky? Okay, if we're a little bit shaky, that's good because we're going to do some more practice with it in a couple slides. So we'll look at those couple slides for practice. Where we ended, what was the day? Tuesday. Where we ended Tuesday was looking at these oxidation numbers, and I believe we've addressed all of them. Okay? It was right at the tail end. Do you have any questions about any of the oxidations that were assigned on Tuesday for these? Once, twice, good luck. Okay, which then sets us up for kind of our summary. So we can track the transfer of electrons by assigning oxidation numbers. The oxidation numbers or oxidation states officially apply to our atoms. So in my general philosophy, I would argue you should always solve for them. So always calculate your oxidation states and your oxidation numbers. Okay? And yes, that does mean in some cases you seem like it's a stupid calculation because it's very simple and trivial. But if you're in the mindset of always having to calculate it, that should help ensure that you don't make a simple mistake and misassign your oxidation states later because you just said what it was. Okay? A change in oxidation number results or signals that we have a redox reaction, which then means once we've identified that our oxidation states have changed, we can look beginning to end for our reactions and determine what species was oxidized and which species was reduced. Okay? I would argue what you're looking at is not oxidized and reduced first and foremost. You're looking at the loss of electrons versus the gain of electrons. Once you've established that, you can then go through and say that you have oxidized or reduced. Kind of make sense? We've got example equations written underneath that can potentially help us. So if we're looking at something that is oxidized, what happened to its oxidation number? It increased. Okay? It increased or it became more positive. We have to be careful of saying it became positive because it didn't necessarily have to become positive, but it does need to increase. And if we're looking at a reduction, what's happening to our oxidation number? Our oxidation number. One increase, the other one must decrease. So we can look for those oxidation states, or sometimes we can get away with charges to help us manipulate. Technically, what I've circled, both for M and A, are the charges, not their oxidation states. Okay? Again, sometimes the oxidation states equal the charges, sometimes they don't, so we do have to be a little bit careful. Okay? The last thing that we can do if we're looking at a complex molecule is the oxidation numbers for each of those individual atoms has to total up to be the overall charge for the individual molecule. And since the overall charge is always given to you, you can cross-verify that your calculation was correct. Kind of make sense? Okay. This sets us up with, hooray, a blue box. This blue box should be a relatively easy one to do because you've already done the work for this, because on a previous slide on Tuesday, you went through and assigned the oxidation states for each and every single one of the atoms in each of those compounds. What you now need to go through and do is decide what was being oxidized and what was being reduced. So talk at your tables, see what you can come up with, and we'll talk through a couple ways to address this. Ready to move forward? In moving forward, I showed some of the work. So for that very first carbon, we look at how many electrons it brought in. Okay, initially, it's valence, so carbon had 4 valence. minus the number of electrons it owns. To determine the electrons it owns, we look at each of the individual bonds, and we look at the atoms on either end of it. Whichever atom was more electronegative owns those electrons. So we have to know our electronegativity trends. Carbon is closer to fluorine than hydrogen is, which means carbon is more electronegative. So carbon's going to own all of those bonds around it. Each of those lines represents 2 electrons, which means there's 8 electrons the carbon owns. So we're looking at 4 minus 8. We should get a negative 4 for our carbon. Okay. If we go through and look at the oxygen on the reactant side, our O2, oxygen brings in 6 valence electrons, and then minus what? Okay. For sure, each of those oxygens, let's just pick one of them, we've got those 4 electrons, but then what happens in between? Well, first and foremost, how many electrons are there? There's 4. That's 2 lines. Each line represents 2 electrons, which means we've got 4 electrons in there. But now the question becomes, where do they go? We look at the electronegativities, oxygen versus oxygen. Since they're the same, they equally divide up those electrons. So each oxygen gets 2 electrons from the bond, which means our total comes out to be 6, and our oxidation state or number comes in to be 0. Make sense? Okay. Dealing with what's oxidized and what's reduced. Okay, so what I would go through and do, and this gets pretty obnoxious and pretty hairy, and we'll see it gets worse later on when we hit another example, but what I would go through and do is look to left and right, and see what changed. So I would start with hydrogen because hydrogen didn't change. It started at a +1, it ends at a +1, so I don't need to worry about it. But if I go through and look at the carbon, I go from a -4 to a +4. It did change. How do we go from a -4 to a +4? What did I have to do? Okay. And this becomes an interesting one because you're going, oh, it's positive. It's becoming more positive. Therefore, it must gain things, right? Because that's positive. Except, what are we gaining? The only thing we're allowed to move around are our electrons. And if we gain electrons, our charge, our oxidation state becomes more negative. So we're not talking about gaining anything here. We're talking about losing. So this is the loss of electrons. Okay? And because we like animals and living things, we'll go through and say the loss of electrons is oxidation. So what happened? Our carbon was oxidized in the course of this reaction. Okay? And we're looking at the oxidation states to determine that. Okay? If it was oxidized, what does that mean also had to have happened? A reduction also has to have happened. So if we think through the abbreviation when we talk about these, we'll call them redox. We don't call them just reduction reactions or just oxidation. When we're looking at an overall reaction, we're referring to it as redox because both reduction and oxidation must happen. Okay? So if I identify that one is oxidized, I know that something must be reduced. I've got to double back through my equation and see if something was reduced. So now we could go through and look at our oxygen. What happened with our oxygen? Went from a 0 to a -2. That had to be a gain of electrons. And since we know that lions gur, we would know that that gain of electrons was reduction. Kind of, sort of? I'm not sure I would necessarily argue that this is brute force because this is probably the approach that you should take when trying to determine oxidized and reduced. Okay? There is sometimes a shortcut that you can run with this. And that shortcut comes back to what we said was the history of our terms, oxidation and reduction. What was the history? I don't listen to history. History is boring. History gives us an answer without having to do any of these freaking calculations. What does oxidation sound like? Oxygen. Okay? So when we're talking about oxidation, what did we do? Increased the bonds to oxygen. So let's take a look at that carbon. Carbon has, on the reactant side, how many bonds to oxygen? Said another way, we find the carbon, right, on the reactant side, Ta-da, there's my green carbon. How many oxygens do you see around it? Perfect answer. None. There's no oxygens connected to it. I can now go through and look at that carbon on the product side. How many oxygens are connected to it? 2. What did you do to the amount of oxygen bonds? You increased them, which means carbon was oxidized. It comes right out of the definition. Okay? That can help us with this statement. And since we're looking at these chemical reactions, very commonly we have 2 reactants. Okay? Sometimes we'll encounter 3 or 4, but commonly we have 2 reactants. And if one was oxidized, what had to happen to the other? It was reduced. We have an internal check to be able to answer the question, what is being reduced in this reaction, without having to do any calculations. But you did have to understand something about the history of these terms. Sir?
Could you also say that since the oxygens are bonding together, they then have less bonds to oxygen?
Yes. So if we go through and look at what happens to the oxygen, okay, it has 2 bonds to oxygen in our reactant side. How many bonds to oxygen do we have on our product side? None. So what happened to the bonds to oxygen? They were reduced, which means the oxygen was reduced in the course of this chemical reaction. Okay? So we can use both aspects of that to come to our oxidized or reduced. Kind of make sense? Okay. So this introduces the next kind of painful aspect behind this. We're going to encounter other terms. These other terms are oxidizing and reducing agents. Okay, this is ultimately a language thing. We're conjugating the word to mean something else. So oxidation or reduction are adjectives, and reducing and oxidizing are adverbs. By changing the language around, should that change any of our labeling? We would assume not, except things get hairy. So, from the previous example that we had, what happened to the carbon? Okay, it was oxidized. It lost electrons. What happened to the oxygen? Doesn't really matter where we go. I'm going to go to the water this time. Okay, it was reduced. It gained electrons. Since we're switching this context from being an adjective describing the thing that happened, CH4, it lost electrons, I now want to describe it as an adverb. What did it give those electrons to? Oxygen. Okay? It's forcing oxygen to accept those electrons. So what did the CH4 do? It forced something else to be reduced. Okay? And I could go through and say, well, it caused something else to be reduced, but instead of using a whole bunch of words, we try to condense that down, and we would instead refer to that as the, reducing agent. Well, it wasn't reduced. We're not talking about what happened to it. We're talking about what it happened or what it forced to happen on something else. The CH4 is the reducing agent because it caused something else to be reduced. Okay? We have to keep those terms in line. So when we go through and do these reactions, you will typically see lots of arrows when I go through and do these things, because I'm going to get all my oxidation states in a row. Then I'm going to go through and say what happened with the amount of electrons. Then I'm going to say that that meant oxidation or reduction. And then I'm going to say it's the agent. All of those things get layered in. Okay? Even if the question wasn't asking all of that information, I immediately reflex into doing that, mainly because I'm trying to keep it straight. And particularly if I encounter questions that have lots of parts, like, I don't know, our quizzes, your very first question may only ask what species lost electrons, but guess what the last question could ask? What species was the agent, was the reducing agent? And if I've already launched into my process of just let's get this information down so I don't have to worry about it anymore, I already have my answers written, and I can now answer every single one of those parts without having to double back and do a whole bunch of back and forth. Does that kind of make sense? Okay. Is the language confusing? Hell yes. Okay. Again, this is why I would write it down to help minimize that as much as possible. The thing that was oxidized caused something else to be reduced. It is therefore the reducing agent. Yes, sir?
Are oxidizing and reducing agents just in the reactant side?
Okay. And if we want to talk about our agents, they're the thing that's causing. Okay. And we look at a chemical reaction, what's the thing that's causing anything to happen? Reactants or products? Reactants. Reactants are the only thing that cause something. Products are the result of said cause. So when we label our agents, they will only be labeled on the reactant side of the chemical equation. Okay? Similar concept, but flipped from when we talked about the conjugate acids and bases. The conjugate labels we put on the product side only. Okay? Or at least we should. Not all people do that. Kind of makes sense? Okay. And that was a blue box, so sorry, I explained it for you. So why is this stuff potentially useful? Redox shows up all over the freaking yin-yang, so you're going to see it everywhere. Okay. But one of the hopefully not relevant to you places that it shows up would be a chemical breathalyzer test. So if people happen to be out drinking and then got into a car and drove, you may encounter something of a police officer pulling you over and requesting you breathe into their device. Okay? And what they're doing is a chemical reaction. Alcohol in your breath will cause a color change because the alcohol reacts with the chromium, okay, in dichromate, and it turns into chromium plus 3. Chromium plus 3 has a different color than the dichromate. Why is this special? No police officer has to take any chemistry class. They just have to know yellow means good and green means jail. Okay? Real simple. Okay? And they don't have to understand anything behind that. What's happening is a redox reaction. Why would you care about that? Not that anybody would necessarily do this, but if you know how a test is run, you also know how it can be circumvented. Okay? And you're like, oh, that's so silly, Mike. You would never do that. But if you had access to the test, what would you do? Or any of your quizzes? You would look up all the answers, and when you took the quiz, you'd have a perfect score, right? You drone the exact same system there. If you know the questions, you'll figure out the answers, and you circumvent the point of whatever the test was trying to do. Okay? Should we go through and do this one for oxidation? Actually, I'm trying to decide. Did I make the class do this? Oh, yeah. Okay. Questions about this before we actually do the calculations? For the record, I am not condoning, nor am I saying that there is a possible way to get around this test. I'm just saying that if you know it, you now increase the odds of being able to figure out how. Make sense? Please don't ever put yourself in a situation where you have to have this test happen. Okay? So now that we've got an example, let's go through and decide what was oxidized, what was reduced in the reaction, identify your oxidizing agents and your reducing agents. Okay? Within this context, we've now already addressed multiple ways to go through and determine all of this information. Okay? One of the things that's kind of caveating this is it says right out of the gate, you need to determine the oxidation number of each atom in the reactants and products first. Is that true? Do you need to do that? Okay? For people that were listening, no more than 5 minutes ago, no, you don't. Because I gave you a method to work your way around that process. Okay? If you weren't listening, cool, determine the oxidation numbers. Okay? Even if you were listening, I would argue you should go through and determine the oxidation numbers of each atom present. Okay? Within that, we still have two ways to deal with oxidation numbers. You can go through and determine the oxidation numbers from the formula. You can also determine it from the structure. Because there's two ways, guess what you might be responsible for on a quiz? Both ways. So you should ensure that you know how to do both. Okay? Feel free to start working through this. It takes a little bit of time to process, but you should be able to pull it together. And based on what I'm seeing you all working on, I may make changes to how we present it. Okay, so we're getting a lot of people buckling right around the chromium for our CR207. So let's go back and review our rule. So when we're looking at our oxidation numbers must add up to the overall charge on the molecule. That's what you leverage. Okay? How do you leverage it? Well, let's start going through some examples with this. Okay? So first and foremost, it looks like people are okay going through and calculating the oxidation states based off of the valence electrons minus the electrons owned. Okay? That process, fantastic process, works when what? When you have the Lewis structure. Without the Lewis structure, you cannot use that process because you don't know what it's bonded to be able to decide what electrons it owns. So you can't calculate half of your formula. Okay? Why is that going to become important? Well, because there's two ways to go through and determine oxidation. Let's look at our structure first. We've got 2 carbons in this structure, right? So let's take a look at carbon red. Carbon red comes in with 4 valence minus how many electrons does it own? It owns 7. 2, 4, 6, and then it owns half of that other bond, which means the oxidation number is -3. Okay? Did anybody, based off you struggling to deal with the oxidation number for our chromium, I'm going to bet nobody used the formula to solve. Did anybody use the formula to solve? For our carbon? Okay, so let's walk through that. Because I saw a couple people, say again?
I started to, but then I got stuck because it was C2 and then it was supposed to be a 5, and so I knew we could do 2.5.
Okay, so let's go through and look at what that formula means. That's what we just went back to. The oxidation numbers, all of them added up, must equal the overall charge. Okay, so I look at that formula. How many carbons do I have? 2. Do I know its oxidation number? No. Remember, always solve for it. So it's X. Okay? Plus, how many hydrogens do I have? 6. So the formula that was given to us is a bit obnoxious because the formula is given in a structural formula as opposed to just a standard formula. What is the oxidation number for hydrogen? Always solve for it, which means I don't know. It's Y. Plus the oxidation number the number of oxygens, there's 1 oxygen, times its oxidation number. Damn, I have to solve for it. Z equals 0. What problem does this create? 3 unknowns, 1 equation. We can't possibly solve that. So how do we solve it? We fall back on some of the rules of doing oxidation numbers the long way. And in the long way, we think about their electronegativities. Oxygen, the second most electronegative element, is going to have what for an oxidation state? -2, because what's it going to do in all cases? Grab the electrons. All cases? No, not all cases. When is a not all case? When you have the oxygens bonded to each other, or when the oxygens bonded to fluorine. Those would be our counter exceptions because there the electronegativity isn't polarizing. Make sense? Yes.
Did product also an exception?
We'll come back to the product potentially being an exception, and I bet what you're looking at is your formula. You're not looking at the formula, it won't be an exception. If you're looking at the structure, you shouldn't have encountered an exception. Okay? So we could sub in that.
Isn't it X, not Z?
Nope, because we said it was the oxidation state for oxygen was a -2. There was only one oxygen, which means it was Z. Okay? That fixes part of our problem, but we still have two variables, one equation. How do we solve? Okay? Well, we can think about hydrogen just as much as we could think about the oxygen. Okay? So compare the hydrogen to the carbon and the oxygen. Okay? Hydrogen can't be bonded to itself in the formula, because if it was bonded to itself, that would be the end of the structure. Hydrogen can only have one bond, which means the hydrogen must be bonded to carbon and oxygen anywhere within the structure. This is just using the formula, by the way. Is hydrogen more electronegative than carbon or oxygen? No, which means what's going to happen to it? It's going to give up its electrons, which means its oxidation number will be +1. If for some reason you had a chemistry class that I would argue was potentially more appropriate, though not following our competencies, where they had you calculate oxidation numbers, there's a couple rules that usually come into play. One of them is that oxygen always has a -2. We've already addressed that's not true. Okay? It's true most of the time. And the other rule they typically tell you is hydrogen is a +1. Again, not always, but most of the time is a +1. And if you memorize those extra pieces, now what happens to your expression? I get 2x plus 6 minus 2 equals 0. Right? Did I do that math? All right, so now I can say 2x equals -4. Yeah? And I get x equals -2. What did I say x was? That was the oxidation state or the oxidation number for carbon. What did we do in red? We did the oxidation state for carbon in red. And those numbers are not the same. Ooh. So clearly one of our methods is wrong. No, there's an underlying assumption in one of our methods that may not be inherently obvious yet. Okay? So let's go back to our structure and calculate the oxidation state for the carbon, the blue carbon now. It comes in with how many valence? 4. How many electrons does it own? 2, 4, 5. It owns none of those because oxygen takes them all away. So I get 4 minus 5, which equals -1. Also not a -2. What the hell is going on? What does your formula assume? Sort of. Your formula is taking the average oxidation state in your compound. Okay? If we were hoping it was all the same, we would assume that the oxidation states were all the same, that they were equal. Unfortunately, they aren't always equal, and it can just be the average depending on your structure. Okay? What is the average of -3 and -1? -2. There it is. So these two methods do actually align, but they're coming from it from slightly different angles, and we're making certain assumptions within it. Depending on what you're trying to do, those assumptions could be false. Okay? So which one's more correct? I would argue neither one is really more correct. It's going to come down to what the question asks and what the question provides. If the question is providing a structure and you tell me -2, you're wrong. Because you're now saying both of those carbons have the same oxidation number, and that's not true. But if you're given the formula, you have no context for how they're bound, now you're going to have to say -2, and you're going to provide effectively the average oxidation number. Does that make sense? So this is a tricky question because it provides two pathways to get to an answer. Depending on which pathway you take and the phrasing of the question, you could get wrong answers. So you have to be very careful to pay attention to what pathway is most appropriate for your situation. Does that make sense? Okay? Yes?
How'd you solve for Z again?
What was Z? That's fine. So if we remember our formula in black, we started with our number of carbons, then we moved to the number of hydrogens, and we moved to the number of oxygens. So Z is the oxidation state for oxygen. How do we know oxygen is going to be a -2? Really two approaches to it. One, you say, oh, I'm just going to memorize oxygen as a -2. Because it usually is, but why is it usually? Because oxygen is the most electronegative element for most of our systems. Okay? Which means when we go through and look at its bonds, it's always going to take those electrons. Okay? Unless it's bonded to oxygen or fluorine. Does that make sense?
So then are we assuming that to just the formula that each atom only has one bond when we're doing the calculation?
So if we're looking at our formula, can we do the valence route? We'll call this our valence route, and we'll call this our total route. Given the formula, can you do the valence route? You have no context to know anything about bonding, so you can't go the valence route, so you're not looking at bonds. There's no evaluation of bonds. If you're given the formula, the only thing you can do is the total route. Okay? And there you do have to make some underlying assumptions. Does that kind of help?
Yeah, I'm just thinking, because like the -2, we're just assuming that that oxygen only has one other bond, and that's why it's taking.
We're not assuming the oxygen has only one other bond. We've made no assumptions about its bonds. 0. In this total route, we have no context about how many bonds the oxygen has. Absolutely none. Okay? And for the record, to get a -2, it could have 1 bond, it could have 2 bonds, it could have 3 bonds, or 4 bonds. All of them are going to result in oxygen with a -2. Okay? As long as each of those bonds is not to oxygen or fluorine. It will always come out to be that -2 because it's going to take those electrons. Okay, so there's no assumptions made about any of the bonding within that system. Okay, the only assumption that's made is that if there's more than one atom, they all have the same oxidation number. Okay, or at best, we're averaging them.
How often, because if you look at the CO207, that's a lot of oxygens.
Yeah.
They could be bonded to each other. Who knows?
So, and that's where you would go through our standard assumptions, that oxygen will always have a -2.
Okay. How often would it be the case that it would bond to itself in this structure?
When would you know oxygen was bonded to itself?
In a little structure.
There you go. Okay, or there's one other case. Because I can give you a formula, and I'm guaranteeing you can tell me that oxygen was bonded to oxygen. Is oxygen bonded to oxygen in ozone? Yes. Why? There's literally no other element. It has to be bonded to oxygen. Okay? And if we go through and run that formula to get the oxidation state, we would assume all the oxygens have the same oxidation state. If we look at the structure, they don't. Okay? So you'll come to slightly different conclusions depending on what you're starting your framework with. Kind of make sense? Okay? And I believe what you were trying to tell me is what we were doing in black. You just did it in your head. I guarantee it's what you did. Guaranteed. 100%. Okay? Because what was the example you pointed to? CH4. And you said, well, hydrogen has a +1.
What we did was every single element had a different number to it. And then we just, like, I don't know how to describe it, but C had a number, C2 had a number, H5 had a number, O had a number, and H had a number. Like,
You mean literally the oxidation states. But you have to solve for them if you...
It's significantly easier. I'll learn it and I'll come to the next class and tell you.
You can try. I guarantee you it's the same thing. 100%. There is no other way to do it.
We were involved in no structures at all either. I mean, I guess
Because what you did was this. Guarantee it. What you did was in black. Okay, so backtrack through. Maybe I don't want to erase that. Let's get rid of that total formula. Actually, I want that total formula. Crap. Let's get our summary. We're just going to go through our summary. Carbon, for that first one, we got a -2 on average. Our hydrogen, we come in at a +1. The oxygen, we come in at a -2. If we go through and assign based off of valence, the carbon came in at a -3. The other carbon came in at a -1. And then we had our hydrogen +1 and our oxygen -2. Somewhat soothing. What happens with our dichromate? Well, in the case of the dichromate, we cannot do this structurally. We must do this in the total format. How many chromiums are there? 2. I don't know its oxidation state, times X. Plus, how many oxygens are there? 7. I don't know its oxidation state. This equals -2. It has to equal the overall charge, so we have to pay attention to that upper right-hand corner. Okay, once we have our system set up, we can now go through and say we have to assume the oxygen comes in at a -2. Okay, we have no other way to go through and solve this unless we make that statement, which then means we get 2x minus 14 equals -12. I get 2x equals, ignore what I said, I think I wrote it right, 2x equals 12. And I get x equals +6. Okay? If you went through and did nomenclature at some point, okay, theoretically back in 151, what you'll notice is this process should be very similar to what you did with nomenclature for balancing out individual ions in an ionic compound. That's because it is the same thing. We just called it ionic charge there incorrectly. It's actually the oxidation state. Right? So our chromium comes in at a +6. We can then go through and look at our product. How do we want to look at our product? We can look at this compound. Okay? We've got 2 carbons. Ben, come on. 2 carbons plus, what is that, 4 hydrogens times Y plus how many oxygens? 2 oxygens, whoops. Times Z, this then equals 0. That's the overall charge. 3 unknowns, 1 equation, that's a problem. We assume our Z comes in at a -2. We assume our Y comes in at a +1. We can then sub that information in. I get 2x plus 4 minus 4 equals 0. Did I do that right? Yeah, it just looked kind of weird to me. Okay, and we get 2x equals 0, and we get x equals 0. Okay, what happens with the last one with our chromium? What's its oxidation state? Well, how many chromiums are there? 1 times its oxidation state, I don't know what it is, has to equal the overall charge. 1 times x equals +3, x must be +3. Do I have to write that workout? No, you don't. Okay? But again, it's trying to emphasize the fact that oxidation state is not charge. Because as soon as you start skipping that step, you start falling into the trap of assigning oxidation or charges as your oxidation state, and that becomes problematic. Okay? There was a question about what's happening with our product, with it not working out. So let's take a look at that at our red. Color coding was bad. Let's make our chromium a +3. We'll get rid of that work. Our red carbon has 4 valence from our structure. Minus how many electrons does it own? 7, which equals -3. Did it change? No. How do we know it didn't change? Look at the structure. Nothing changed. It's still bonded to 3 hydrogens. It's still bonded to a carbon. Nothing changed. Its oxidation state shouldn't have changed. If we go through and take a look at the blue carbon, what's happened? Ooh, it changed. Okay? So it comes in with 4 valence. How many electrons does it own? 1, which equals a +3. What's the average of -3 + 3? 0, which happens to be the exact oxidation state we calculated using the total formula format. Don't you love it when it all matches? Okay? So that's the point in recognizing this. You can go through and be very specific and go atom by atom, or you can be kind of a step back from a formula and just look at your averages. Okay? Kind of makes sense? Did you find out what went wrong, Emily?
Yeah, no, I counted the double bond as one accident.
Oh, yeah.
This might be a dumb question, but where did all the oxygens go? Or like, why is it not balanced?
And I think Maya mentioned that too. Weight. Okay, so let's finish out the rest of the question because we're asking about what is reduced or oxidized within this reaction. We've got all of these numbers, so what we should be trying to do is evaluate the differences between them all the way through our process. Okay, our hydrogen was a +1 in the reactant. It doesn't matter which way we did it, but it came in at +1. What was it in the product? A +1, so let's ignore our hydrogen because the hydrogen did absolutely jack within this process. Okay, so we don't care about our hydrogen. What happened to the carbon? It went from a -2 to a 0, which means it lost electrons. Loss of electrons is oxidation, which means it's our reducing agent. Okay? If it's the reducing agent, then something else had to have been reduced. So we could go through and look at the oxygen. What was the oxidation state for our oxygen? I knew I had to do some other element. On the reactant side, it was -2. Okay, wherever the oxygen showed up, it was -2, which means what can we do about the oxygen? We can ignore it. Nothing happened to it. All right? So we've looked at the carbon, the hydrogen, the oxygen. The only thing left is chromium. That's right. What happened to the chromium oxidation state? We went from a +6 to a +3. Okay? Since the number went down, I would immediately call that reduced. Okay? But officially, how was it reduced? See, and there's that wording coming into play. Reduced, so it must lot. No, because it's an electron, and electrons are negatively charged. So this is a gain in electrons, which is reduced. That matches, right? Which means it was also our oxidizing agent. Okay? The agents officially apply to our reactants. I see you might be a couple questions back. We'll see. Okay? So our dichromate, the Cr2O7-2, is our oxidizing agent. The ethanol was our reducing agent. And we've got all of this glorious work, which looks like an awful mess here, but I'm constricted in space. Theoretically, you should be able to flow this kind of downwards to be able to see what's happening and make those ties a little bit more cleaner on your paper. Kind of, sort of?
So, I guess I'm kind of just mentally figuring it out is like, so when it's going from a -2 to a 0, so it's going up even losing electrons, but when it goes from a +6 to a +3, where it's going down, it's gaining?
Yeah.
Okay.
And that makes absolutely no sense, right? If I go from a 0 to a +2, I'm losing. What? What are you losing? An electron, which is negatively charged. So you're going from a 0 to a +2 because you're losing negatives. A loss of a negative is a positive. It's the double negative coming in, biting you on that one, and then the other, you're still gaining, but you're gaining a negative thing. So you have to be careful with that minus sign. This is not the first time I've said you need to watch out for minus signs. Okay? And it's going to happen again in this lecture. Okay? In every single one of our units, we've had issues with minus signs. You have to keep track of them to ensure they don't screw up your calculations. Okay, and be real careful. Okay? Again, I have problems with it, which is why I always write out all of the gory information detail. Okay? Which in a lot of cases is absurd and unnecessary. Okay? At least for how I was given quizzes. Okay? For the context of how you guys are given quizzes, I would fully expect that if you wrote out all that gory detail, you will have answered 4 or 5 parts.
So when doing this final comparison to figure out which is oxidizing and reducing agent, are you always going to use the average by the 2 carbons and not always going to use the average?
So there's an interesting question. Should I be using the average or the actual? Do you get a different answer? No. Okay? So ultimately, it's not going to matter. Okay? When should you use the actual? When you have the Lewis structure. That's it. Okay? So if you're given the Lewis structure and we ask what happened to it? What was oxidized? And you tell me the red carbon, you're wrong. Because what happened to the red carbon in this reaction? Nothing. It stayed the same. Okay? But I can only ask the question, the red carbon, because you have the Lewis structure. Delete the Lewis structure, I can't ask that anymore. Okay? Because you would need a structure to be able to manipulate that. Does that make sense?
Yeah.
So yeah, this slide is really nice and really bad all at the same time because we've got 2 different kind of competing processes to how we could go through and solve. And it all depends on the context of what you're given. We're given everything, which means we got to look at everything. Okay? Other questions? Okay. A question was brought up, okay, early on and then a little bit later. If we go through, can I delete everything? Because there's a lot of stuff up there. Let's clean it up. If we go through and try to, and I'm even going to clean that up, and we look at this chemical reaction, what you might notice is that it's not balanced. Okay, right? If we look at the reactant side, how many oxygens do we have? You got 8. How many do you have on the product side? 2. So this is missing something. Okay, it's missing a significant chunk of information to go through and balance. Admittedly, I'm really freaked out right now because I would argue balancing these kind of chemical reactions is something that you're responsible for. I don't think it's in the slides. Okay? I would bet it's in Alex. Okay? Has anybody started into the Alex homework? By the way, no one asked this question with the other class. Maybe because they were just like, oh my God, there's too much going on. Mike, stop talking. Has anybody started the Alex to see if you're balancing redox reactions? It's something that I would have to review to be really confident on it. Okay, but real quickly, you can go through and look up the process for balancing redox reactions that do not appear to be balanced. And typically what happens is to account for that missing oxygen, what would you do? Whoops, sorry, I erased the stuff I wanted. We had 8 oxygens over here, and we had 2 oxygens over here. We would need to add more oxygens. How do we add the oxygens? As water. Okay, and you go, what? Not 2. Not 20, sorry, 2. And not 8. Man. Oh, it's not 20, it was oxygen. Okay, we had 8 oxygens, let's do it this way, and 2 oxygens. Make sense? Okay. I'm going to add water to the reactant side, because what does water have in it? Sorry, that's not the reactant side. It's the product side. I'm going to add water because water has oxygen. How many waters do I need to add? 2? How many oxygens do I now have on the product side? 2 plus 2 would be 4. Is it balanced? No. How many oxygens do I need to add? 6. And what some people may be looking at is, well, yeah, you added the oxygens, but what else did I add? I added a bunch of hydrogens, and there are no flicking hydrogens on the other side for me to go through and deal with that. That's why you go back to the other side and you add hydrogens. You'll add it as H+. How many H's do I need now on the reactant side? So we go through and evaluate our hydrogens now. I really hope I'm doing this right. I literally have not balanced these in a very long time. 1 initially over here, hydrogens. We had 1 plus 10?
No, you need 10 on the other side.
Oh, okay. 1 plus 12, right?
On the other side?
No, I'm trying to, how many hydrogens do we have on the product side? You're doing good math in your head. Oh, 4 plus 12. It's not 1 hydrogen, it's 6 hydrogens over here. 3, 4. 6 times 2 is 12, so 4 plus 12 is 16. Yes, you're right. So I would need 10 H plus over here. Okay? So to go through and account for those oxygens, I add water to one side of the equation. And I just noticed something that I missed that I'll come back to in a second. Okay? Once I've added the water, I'll now go to the other side and counterbalance it with H+. Okay? This is now saying I'm balancing the reaction under acidic conditions, because what have I added? H+. Okay? What if I wanted it under basic conditions? Well, but how do I get it to basic conditions? To get it to basic conditions, I'm going to add hydroxides. Whoops. That 10 and the O is killing me. 10 hydroxides to both sides of the equation. What does the hydroxide do in the presence of the acid? Neutralize to become 10H2O. I then have hydroxide on the product side, but I also have motherfucking water on the other side of the equation. So what do I got to do? Subtract H2O from both sides of the equation, and I would get 4H2O. Now I've got hydroxides on the product side, and now I'm under basic conditions. And you're like, this sounds like a crappy convoluted process. Kind of is, okay? But you go back and forth for each of those systems. You start balancing under acidic conditions. You add water to whatever side of the equation you need to balance out your oxygens. To the flip side, you add H+, if you're now under acidic conditions. You want basic conditions, you neutralize the H+ by adding in enough hydroxide to both sides of the equation, and then you got to balance things out by canceling like terms on both sides of the equation. Okay? Before we point out another failure in what I've done up here, do we have questions about that? Are you going to point out the freaking failure?
I'm not going to put on the
You probably are.
No, I'm not. I was just wondering if we're going to do anything. You know for sure we have to do something.
I do not. Okay? So this balancing process, I would bet shows up in Alex.
Oh, I see. Okay.
Okay? And I also don't know that. But it's what I would have called standard content in 152, so I would expect it would show up in Alex because Alex is standard content. I don't think I saw this balancing process anywhere in the slides. So what I'm trying to do is set you up for potentially being able to answer Alex questions.
Regarding Alex, I was just looking, it does not look like they're balancing that kind of stuff, but there is some balancing of like, it was saying like, doing the half reactions.
Yeah, we'll get to half reactions in a bit.
That's, I haven't seen anything specifying that.
Dealing with acidic or basic conditions?
Yeah, I was like, I do have block forms unfortunately, because it's something
Yeah.
compared to the previous, but I'm not seeing anything that I'm talking about.
Yeah, so hopefully we don't have to worry about acidic or basic conditions. If you see that, realize this is a new system that you're doing some convoluted things on. Does that kind of make sense? What's the part that I screwed up? Yeah, before you do acid and basic conditions, you got to make sure all your other atoms are balanced, and I forgot to balance the chromium. Right. Thankfully, actually, it wouldn't change much because all I need is a 2 there. And then I would still balance out the same with the rest. Kind of, sort of?
But as far as the quiz goes, unless it's stated to balance.
Unless we see it in the slides, from my experience, if it doesn't show up balancing acidic or basic conditions in the slides, that's not showing up on the quizzes.
Okay, so just assume that that's what you.
Yeah. And unfortunately, I have nothing better. Okay? Once I see a quiz, if I see that show up, we will very suddenly have some lecture content on it.
So by balancing the chromium, is that changes oxidation state?
Nope. Okay, so why does adding 2 in front of the chromium not change its oxidation state? How do we determine the oxidation state? Okay, the charge. So how many chromiums, so and this is going to come into an interesting play on this, how many chromiums are you trying to balance or determine oxidation state for? Okay, there's 2 interpretations. Okay, so let's run with yours because I like yours. I like yours better. Okay, but we can do the other one in a second. I have 1 chromium. 1 chromium times its oxidation state equals +3. What's the oxidation state? +3. But you're like, no, there's 2, because there are 2, right? There's 2 times its oxidation state, now the charge. What's the charge? The charge is going to be +6, because there's 2 of those +3s. So now when I go through and do the math, it still comes out to be the same. Okay? But if you're going to use the coefficients, you have to make sure you pay attention to multiplying that charge through as well. Okay, let's talk about something else.
But in that same context, would it only be bonded to itself, or would it be 0?
If we put 2 in front of it, is it bonded to anything?
No.
Nope. And we talked so long about that I broke the computer. Okay, what is electricity? That's right. Electricity is electrons moving. There's a giant white space here because I have a feeling she wanted to draw something. I have no idea what she wanted to draw, so I'm not going to draw anything. Chemists define it as moving electrons. This becomes an important statement that I want you to be aware of, particularly for those of you that are engineers or physicists. Okay? Because while chemists say it's movement of electrons, engineers and physicists are freaking loopy in the head, and they don't talk about it as the movement of electrons. They talk about it as the movement of holes. What the fuck is a hole? Okay? If I have a metal here with some electrons, right? And the electrons go over here to that thing, what happens in that space? I'm now missing an electron. So what do I have? I have a hole. Okay? Which sometimes will be referred to as positive charges. More frequently, I hear it referenced as holes. Why? I don't know. They're loopy in the head.
I think that's more of a physics definition.
Engineers do it too. They both do it. I think engineers sometimes have a little bit more on the chemistry. It depends on their background. Who taught them what's going on within it. So if your engineer goes through a chemistry path, they'll talk about electricity as moving of electrons. If they move through a physics path, they'll talk about holes. I'm not sure I've ever heard it referred to as protons.
I mean, that's conventional current.
I don't even want to touch that. I'm going to leave that alone. Electricity is confusing enough for me.
No, you do that in physics too.
So, how does a battery generate electricity? Okay. Well, in a battery, we have a reduction side and an oxidation side. What's happening on the oxidation side?
Losing electrons.
Loss of electrons. What's happening on the reduction side?
Gain of electrons.
Gain of electrons. Okay. Note we have this weird yellow stuff in between. What is this yellow stuff now highlighted in purple? A space that no electrons can pass through. More or less. Why does that matter? Well, if electrons could pass through it, what do our electrons do? Our oxidation shuttles electrons to the reduction side. What do we get as far as electricity? I love asking questions where the answer of silence is perfect. Okay? Yeah, you get nothing. By putting a barrier in between, what happens? Well, the oxidation side is going to lose electrons, and the only way it can get to the reduction side to gain electrons is by doing what? Shipping those electrons through a wire. When those electrons pass by a load, I think I did that right, like a light bulb, we get light. The electrons will continue to pass on their way around to the reduction side. Okay? So what we've done is created a diversion in the electrons to allow for us to access the electrons being transferred. When we do this, we call it an electrochemical cell or a voltaic cell. Okay? It's kind of a neat little process. We can do the same thing with water flowing downhill. It's the exact same idea. Water flows down naturally on its own. So what do? We stop it from flowing downhill and only allow it to flow downhill through turbines. Those turbines generate electricity for us. This is the same thing. Okay? Our electrons want to flow from the oxidation side downhill to the reduction side. We prevent that from happening by diverting it through the wire. And it's that diversion that allows us to actually get electricity to do what we want it to do. Okay? Because of this, we're now splitting our reaction apart. We'll look at the reduction side somewhat independent of the oxidation side. And since we're now looking at splitting our reaction in half, we can call each of those reactions half reaction, because half of it is a reduction, half of it is an oxidation. Okay? I apologize for the weird font sizes. It's Google Sheets. Okay? So what's happening when we look at the reduction side? My copper ion turns into copper metal. What was the oxidation of my copper ion? Well, there's 1 copper times, I don't know what it is, equals an overall charge of +2. On the product side, well, there's 1 copper, I don't know what its oxidation is, has to equal overall charge of 0. So the oxidation went from a +2 to a 0. What changed? It had to gain electrons, and gain of electrons is commonly known as reduction. Okay? That's what's happening in that 1/2 of the reaction. The other half of the reaction is done similarly. And what's happening is we're now looking at a loss of electrons. We can see that gain and loss in our half reactions. How do we see it? Well, if I gain electrons, where are my electrons? They're on the reactant side of my chemical equation. And if I lose electrons, where are they found? On the product side of the chemical equation. Okay? This brings up an interesting concept, though. How many times have we seen electrons in a chemical equation? It's only here. This is the first time. Why have we never seen it before? Because electrons aren't stable. Okay? They cannot exist on their own. So when we're looking at the half reaction, we're creating a figment to help us better understand what's going on within the chemical reaction. That's it. Okay? This allows us to see where the electrons are, and more importantly to Emily's question, allow us to balance out the electrons. Because when I add these two equations together, what must be true? I cannot have electrons in my overall equation. So if the electrons don't match, I'm going to have to run that reaction multiples of times to get the electrons to match. Okay? So a voltaic cell uses a spontaneous redox reaction to release this energy. Where have we used spontaneous before? We used it for entropy, we used it for enthalpy, and if we used it for entropy and enthalpy, we've also used it for free energy works, delta G, okay, our Gibbs free energy. So what we're looking at is a spontaneous reaction. It wants to go through and happen, okay? So this is a downhill process. What we're trying to do is leverage and get in the way of it to force this to happen, which means we have to know something about the energetics of each of those chemical reactions to align so that we can take advantage of it. Because if it's an uphill process, it doesn't want to do it on its own, which means the only way I can get it to happen is I put energy in. What's the whole point of the voltaic cell? Try a different way. What's the whole point of a battery? To get energy out. Okay? That's our whole important process. So it has to be a spontaneous process for us to want to use it. Okay? So if we're going to look at an overall redox reaction occurring in this voltaic cell, what do we need to do? Same thing we did with Hess's law and enthalpies and all that fun stuff. Okay? I can take my half reactions, and I can align them. If you're wondering why I'm going fast, there's a couple things that I would like to get to that I'm pretty sure I'm just going to have to accept I don't get to. Okay? I would align them like that. And when I add them up, what do I get? I get copper plus 2 plus zinc plus 2 electrons goes to zinc plus 2 plus copper plus 2 electrons. What do we see on both sides of the equation? The electrons, which means delete. And what do we have? The overall equation. Okay? That's the point of this process. Which way are the electrons moving through the wire? Okay? Well, let's guess. I'm going to say they go this way. Does it make sense for the electrons to move that way? By the way, this black thing is the wire, if you were wondering. Is the copper producing electrons? To produce electrons, where must they be? They must be a product. Copper isn't producing electrons. Copper is consuming electrons. Which means if I'm talking about the electron flow, the electrons actually need to go into the copper. Well, what's happening with our zinc? Are our electrons flowing out? The electrons are a product. They will flow out of that side through the wire over to the other side. And if we look at this, what's happening on the zinc? It was an oxidation because it lost electrons. I think I spelled that wrong. And the other side was a reduction. Right? This can help us put all of these labels into the system that help us navigate what's happening with the directions of electrons and all those other things. The last thing, one of the last things we'll go through and do is we'll talk about labeling anodes and cathodes. The anode is where the oxidation occurs. Let's see if I can spell it right this time. Oxidation. Okay. I typically use blue to represent oxidation. Okay. So if I think blue and anox, are there any famous blue oxes? Nobody? Is it blue? Bluebell? Is it a blue? It's a blue cow? Perfect. So if you know the ice cream, Bluebell, there you go. Anox blue. You're tying the an to the ox. What's happening on the other side? Well, the other side must be the cathode then. And it'll be reduction. Red cat. Okay. Could I have said an cathode? Why can't I say an cat? Because we speak the English language and we know to use the letter N after A when referring to a singular thing, it needs to be a vowel in the next word. So I can say an ox, or I would say a cat. So I can leverage the English language to help me with a little system to nail down this device. Okay? One of the things, again, I know you can definitely pack up. We're going to quantify a lot of this energy. That energy gets quantified through a cell potential. We've got formulas calculating cell potentials, and more importantly, because we're relating to delta G can be tied to K, our equilibrium, which then means you can bring in the concepts of Q's and K's into your chemical expression. Why is that relevant? This equation is directly relevant and necessary for solving things in ALEKS this weekend. I assume it's due this weekend. Someone asked me about it from the other class. Okay? We'll double back or start whatever it is, Tuesday, back here with dealing with our oxidation states. But at that point, we are now done.